All right, guys, welcome to Cassandra Lunch 16. Today we're going to be talking about anti-entropy, or what's also known as the repair. Technically, the term is, I think it's just synchronization, making sure everything is synchronized. I'm Raul Singh, I'm platform architect at Anant, and we're a DataStack strategic partner. We try to keep it fairly objective, so we're not just talking about DataStacks. We also talked about Cassandra and other variants. Akui is my co-organizer. If you want to reach out and you want to present on a particular topic, always can use co-organizers to help get speakers, sponsors, inclusive community. So we want people from all backgrounds to come and present, especially from underrepresented communities. We are part of a much larger group of meetups: Data Science DC, Data Innovation DC, Data Visualization, you name it. We cover anything related to Cassandra or Cassandra variants, anything that talks to Cassandra, like Spark, Kafka, could be building APIs on top of Cassandra. Normally, we use this time to have folks who haven't joined us in the past to just quickly introduce themselves. So, David, if you want to just introduce yourself, you know, what your background is with Cassandra, and what you're trying to learn. Sure. And whatever experience that is relevant, that would make sense for us.
Well, so I'm David Nye. I have a small consulting firm with a couple contracts, namely at the FBI. And my experience with Cassandra is back with the Patent and Trade Office. It's been, I don't know, 5-6 years ago at this point. It's been a while. And I hadn't really used it since. Been using other NoSQL technologies, but then I kind of reconnected with Raul and I guess Jay. I don't know if any of you guys, well, he's probably on these meetings as well. Yep. And been talking about Cassandra and supporting Cassandra. So I've been trying to get back into it, honestly. I hadn't worked with it a lot. It was mostly doing Spark queries, but as far as like actual Cassandra and administrating Cassandra, none of that. Really didn't do much of that. I just understood that it was a NoSQL database. So I've actually been taking the 8-week Cassandra workshop course. So I've been doing that. About halfway through the homework, so I do need to catch up on that. I just have other, you know, so many other things, but I'm definitely catching up on that, and hopefully try to get certified here in a few weeks, take the test. So that's kind of a little bit about myself, I guess, and my background.
Great, thank you, David. Appreciate it. This is mostly for David, but to catch up, you can go to YouTube, where we have been recording for a while different topics on Cassandra. At least I think from lunch 10 until today, we have a recording, so you can always catch up there too. So here's another set of homework for you. And then there's a bunch of other topics that are in the backlog. Thank you. Group rules: if you have a question, just ask it politely. Actually, if you want it, you can use the chat function or raise your hand. I don't personally mind. Some people that may present here might mind, but you can just politely ask. DataStax is a sponsor. So is GW, Masters in Business Analytics. We have other kind of local sponsors, a couple from Chicago, a couple from DC area, because we've been doing this, organizing this meetup in DC and in Chicago, and because of COVID, we've just consolidated this into a weekly series. I updated this deck, but this is our current set of organizational sponsors with Data Community DC that funds the nonprofit known as Data Community DC. You can go to it at datacommunitydc.org. Also, you'll see and hear the term DC2. This Data Community DC, DC squared. That's what DC2 is. Any announcements from the group on? I have a couple of announcements of webinars coming up from Anant. Okay. All right. So as we've mentioned in the past, DataStax weekly workshops that David also just mentioned, he's been attending. This weekly lunch call is ongoing. And DataStax, we worked with Cedric, and we'll be adding a few more presentations like the one we did in the past about building the API with Cassandra on top of Astra. So the next topic we'll be doing on is streaming into Cassandra from Kafka. Actually, Ryan is on the call today. He was working on some of the code for that. Upcoming, this was yesterday. Today we have Spark and Cassandra for machine learning for model selection tests. And then tomorrow there's a really fascinating talk on using open source notebooks and Cassandra. I spoke with the presenter yesterday, Arkin, and I learned about 2 notebook tools that I had no idea existed. So Quix and Polynote, which are fascinating. You can always find more events on our event page, and of course on the Meetup page. All right, so getting right into it, the repair process or the anti-entropy process is little understood, and this is one of the reasons why Cassandra is a scalable database, is because it eventually keeps everything consistent, even if certain replicas are off sync, right? There are a few strategies on how Cassandra keeps everything in sync. One is called hinted handoff. What hinted handoff means is that if a node is seen as down, the other nodes take the mutation or whatever the data update, right? And they store a message. This used to be stored inside a Cassandra table, which then caused a bunch of issues. So then now this is stored as hints, as files. And then when the node comes back up, it will take all of those hints. The default window is 3 hours. So a node can be down for 3 hours, and as long as it's meeting the consistency requirement, mostly people do quorum or local quorum, that gives a lot of leeway. So if you have 3 nodes in the data center, sorry, you have the replication factor of 3, and you have 9 nodes, one node could be down, and as long as you're doing local quorum or quorum, you're not going to have any issue. So this window is 3 hours. After this, the system will start saying that I'm dropping these hints. It's been way too long. We don't need to keep track of these hints. But hinted handoff is configurable. And if you know that you need to do maintenance on a node, you can extend it, or you can even turn it off. You can say, I'm going to do maintenance on a bunch of nodes. I don't want hints to be piling up. I've tested it in the past that our consistency level with quorum is going to be fine, so you can just turn it off. I have some visuals that accompany this, but I want to talk about the strategies first. The other strategy is read repair. Read repair can be done using async or non-blocking calls. Another one is synchronization, sync calls, which is blocking calls. And what a read repair basically is that when you read data without you specifying any special consistency, there's a setting per table. It's called read repair chance. Okay, and usually what we do is we say DC local read repair chance, and it's like set to 0.1, meaning 10% of the time of all read requests, 10% of the time we do what's called a read repair. We'll talk about what a read repair is, but essentially we'll talk about how it's done. The basis of the read repair says, oh, you're asking for this data 10% at a time. I'm going to go to all of the replicas for this data, and I'm going to make sure that all of them are current. And that's what repair is, making sure that the last write is what is consistent across all replicas of the particular piece of data. There's another one called read repair chance, which if you set it, it will do it across the cluster. So you do a read, it will then go across the cluster. So you have 3 different data centers and a replication factor of 3. It will go to all 9 different replicas and make sure that they're consistent. If you're doing transactional on one side and analytical on another side, the analytical queries may scan all of the data, right? So that may create a load on the other data center. So definitely recommend not doing this. Right? Don't do this unless you know what you're doing. And default schemas nowadays, this is what's set to 0.1, and this is set to 0, or not set at all. The problem I've seen is that people have source control, and in the source control, I'll say the problem is not source control. The problem is that when they export a schema from a single data center development environment, where the read repair chance being 0.1 is fine, and that configuration gets imported into a production environment, which may have multiple data centers, this setting is not good. So you can be as effective if you just make sure that this is equal to 0, and just make sure that this is equal to whatever you need it to be. Maybe it's 2%, depending on the use case. The other way to do a read repair is blocking, and all you do is you say consistency level all, right, in your queries or in your driver. And when you do any read, right, what this will do is it'll automatically repair, because consistency all means that everything I'm getting has to be consistent. So while it's making sure it's consistent, it actually goes ahead and does the repair as well, right? Convenient. Some people actually use this feature to walk and scan the whole table. And in that action, they have made everything consistent and everything is repaired. Right? I say use this if you know what you're doing. Here's a case for why you would do it. Bunch of data is getting streamed in, but you want to make sure that at the end of an operation that the data is always synchronized. So you can do a bunch of writes, okay? And then you can do a read and say consistency all as an asynchronous call, kind of doing a bit of both. That's the strategy that's used. So most people, when they think about repair, they're really talking about no tool repair. Okay, unless you've used read repair or have gone into this and seen a problem, you really don't even know that read repair exists. It just kind of happens in the background. Hinted handoff, again, Cassandra doesn't go down unless somebody's really being, they're not skilled at operating a cluster. We normally don't have, hints or dropped hints. Sometimes when people don't monitor their cluster, a node will go down and they won't know until, a day later, meaning they come back after, Sunday on a Monday. I'm like, oh, wow, this node is down, let's restart it. What they'll have missed out is that dropped hints didn't get sent to that node, that they should probably force a repair to make sure everything is consistent. But again, most people, they know about no tool repair. Repair can be done from a node to say, whatever tokens I have on my node, right, make sure I get that consistent with the rest of the cluster. Another is just make sure that I'm consistent with everything in my data center. So we'll say node to cluster, node to data center, and then you can just do a cluster wide, right? Make sure that you run this process on every node. Okay. To get even more specific, there's incremental. It's called sub-range, where we say take this token range and do a repair on it. and that can be facilitated with no tool repair, given, give it a particular partition range and it'll go do that. You have to be fairly adept at using no tool to understand this. You should be looking at logs. If there's failures, then re-repair that range. But these days, there's tools to do that for you. Off Center used to be available for DataStax community and open source Cassandra. Now it's only a part of the DataStax toolkit. Off Center Repair basically wraps these functions, and instead of doing a massive process, it actually checks to see when nodes are not as busy, and it just does repairs on small ranges until the whole thing is done. It's kind of cool. There is another feature which is called Nodesync. I'm actually going to say this is DataStax, and then this is called DataStax Nodesync. And Nodesync is basically built only in DataStax, but you can set it in terms of how fast you want to sync data. Whenever data is changed, it queues up that, oh, thank you guys. I guess I was not sharing my whole screen. Appreciate that, right? I guess I was just sharing my Chrome window. Can you guys see my workflow?
Yeah, I can see it.
All right, so sorry, I was typing a few things here. Input handoff, re-repair, so no tool repair, and the tools. There's DataStax node sync, and node sync basically when data is changing, it queues up like almost like a hint, but for a node that's up, and says, go ahead and repair this. So if you have a lot of data coming in and you want it to be pretty much immediately consistent across the board, Nodesync is great. Nodesync is not great if you do a lot of batch ingest, because they'll just clog this process up. And finally, there's something called Cassandra Reaper. It's an open source tool. Okay. Which basically means you can use it for free on Cassandra. It also works on DataStax because it's basically wrapping the node tool, and node tool is native to both. I don't know if it'll work on Scala. Technically it should, because Scala also has a node tool interface. It definitely should work on Cassandra as well. So these are the different strategies. And I'm going to now walk through some articles that talk about repair, which are on Cassandra.Link. And when there's a blog post up soon, you'll get links to all of this. So, this article, 3 ways Cassandra keeps data in sync, will walk you through read repair, hinted handoff, and anti-entropy repair, which is basically what is being used when we do no tool repair. Hold on one second. The other articles, we'll go through them one by one. But, this is probably the shortest article about repair that you're going to find, kind of explaining what's happening. And also gets into the deals of what's happening, how can I monitor this? It talks a little bit about read repair. I'll put this in the chat. Okay. Next article kind of gets into the nitty-gritties of what is actually happening in repair. So how does repair work? Well, basically what happens is that Cassandra uses something called a Merkle tree, which is it's also a method that's actually used in blockchain to compare chains of things. In our case, what it does is it keeps a hash of the data, what it is, and so let's say for a particular row, right? If there are two fields, we'll have hashes for the key value, and that row itself will have a hash of these two hashes, and then a particular part of the SS table will get bunched up, and then finally at the whole table level, right? So if no data has changed, right, between two nodes, when we look at a particular comparison of the hash, we won't see any change. But if one of these things changes, it trickles up. So even if this area has not changed, this change will trickle up to here, and it'll trickle up to here, and then it'll finally, we'll know that something has changed. And so when we go down, we don't have to synchronize all of this data. We just have to synchronize here, and then we don't have to synchronize this because we'll see that it's comparable to the other one. We'll just need to go down and change this area of it. And that happens on a kind of recursive basis. So what repair does, it goes through all the different SS tables, and it calculates a hash, and it creates a Merkle tree. And then what we do is between nodes, we compare the Merkle tree. So we don't have to do a comparison on all the data. We just have to do a comparison on the hashes, right? So what is incremental repair? Incremental repair basically takes different SS tables, breaks them apart, which is called a process called anti-compaction. But while it's doing that, it says I've repaired this data in the last, let's say, 10 minutes or so, right? And so then we only are trying to repair data incrementally, not as a whole, okay? But incremental repair has a kind of a side effect, right? Some problems, but generally after the first repair, it's supposed to just be doing smaller and smaller sets of SS tables. But what happened is that in certain cases in LCS, what was happening is in the incremental repair, because these SS tables were getting created at different stages on different machines, sometimes it would cause nodes to just stream data that did not need to be streamed. It was just extraneous moving of information. So that has been fixed, but it's really coming in 4.0. It's not a part of 3.1 or 3.11. So don't use incremental repair unless you're using 4.0, which is the latest and greatest version of Cassandra. So this is a great article on TLP, but also on Cassandra.Link. I don't know why I can't see the link here. Yeah, and I'll send this in the chat as well. All right, moving forward, I want to show you kind of a few of the tools that are available. As I mentioned, Opcenter is one of them, because Reaper is another one. Actually, we can talk about incremental repair improvements in 4 before we do that. So I'm going to move this back here. Here's an older article about just general repair that you can dig deeper into. So incremental repair, as it has been fixed recently, really focuses on kind of like there's a holistic change in Cassandra, in Cassandra 4. There's a whole change in how data is streamed. There's a whole networking layer that's built in, and it's different from the older incremental repair in that it only does repairs after kind of an anti-compaction, and then there's a set of basically tables that are unrepaired. There's a set of tables that are pending repair, and then there are repaired SS tables. This is basically the missing piece that we didn't have in the older incremental repair, was that it was treating, regardless of what the actual thing was doing, ultimately each stage was not recorded. So we ended up having unrepaired SS tables or pending repair SS tables be streamed, and they shouldn't be streamed, right? So unrepaired SS tables, basically stick around, but then as these are pending repair, they get streamed, but repaired SS tables don't get streamed because that data is already there, right? So if you want to read into this a little bit, more, this link also explains how you can check it out with a stress test. And now for the fun part. So Cassandra Reaper is a tool that was originally made at Spotify, and then TLP, which is now part of DataStax, basically continued working on it and open sourced it and then added a really nice interface to it. TLP can run backed on different backends. So it can store the state of the repair in memory or an H2 database. Postgres, Cassandra itself, you can store the repair data, or on Astra, which is the database as a service. Cassandra as a service from DataStax. And there's different YAML files that show you how to do it. It's kind of a no-brainer. If you're using open source Cassandra, you should use Reaper to do repair. Really no reason not to use it. You can do multiple DCs. You can have multiple DCs with multiple Reapers, Reaper instances, like this, right? So great tool. It's also in our Cassandra toolkit. If you just look for Cassandra toolkit, I think we should come up. There we go. So in the Cassandra toolkit, all the best tools that you should be using with open source Cassandra are part of a Docker composition, and then there's other cool things that are in there like Node tool, Node analyzer, and table analyzer, which are being worked on. But if you wanted to just see how this works, you can just pull down this repository and let's see, I believe this Ansible will bring up all the tools that you need on a particular Cassandra cluster. Okay. And then Op Center has gone through a lot of changes. Op Center has a few different features. One is called LCM, Lifecycle Manager. That's not what we're talking about. We're not talking about Op Center monitoring. We're talking about Op Center repair. So these are different components of the same thing. And when you are looking at Op Center, there isn't a lot of configuration in terms of repair. You basically take your largest, I don't know why they don't have a screenshot here. Here we go. You take your largest GC gray seconds and you subtract a day from that. And that's essentially the time that you would say, I want my repair to happen, right? So if your largest GC gray second is 5 days, and you would say, okay, we want the whole repair process to end in 3 days. If you didn't use Op Center repair and you had a large cluster, you would basically be running a cron job at staggered times on each machine to make sure that the repair process finished. Same thing with if you didn't use Reaper, that's what you'd have to do. So if you can help it, just use the tool, right? So then you don't have to kind of spin another set of plates on repair. The other is Nodesync, as I was mentioning. And you basically can just set, I don't know if I can see, here we go. You can set different rates in terms of, what is the rate in kilobytes per second. You can make it high, you can make it low. Basically, the goal is that you want to increase it if a lot of data is changing, and you can decrease it if a lot of data is not changing, because no tool does take some processing time. Right? It does have some CPU footprint and a network footprint for that. You can also set a deadline to say that, make sure that, between two validations of the same data, I want it to happen a particular amount of time. So I don't want more than, let's say, an hour to go by before the data is synchronized. An hour is a long time, but in the scheme of like a really large cluster, an hour is not that long of a time. You can set it to seconds, like 30 seconds, when a lot of data is changing, but just be careful. You'll have to change the throughput rate to be higher to be able to do that. That's basically the repair options that are out there. A lot of people will have different cluster topologies. Last week when we talked about backup, we were talking about the strategy of using, let's say, having one data center with a lot of nodes, and then having another data center with just one node, and that's your backup node. Well, if you run repair on this one node against all of these, then technically we'll have repaired that data center. Right? That's a strategy to kind of keep your footprint small on the repair process. So, repair, anti-entropy, synchronization, all kind of terms that we don't really worry about in the relational world, or even in other NoSQL databases. They're called different things, but in Cassandra, because we have potential of having hundreds of nodes, and there's 3 replicas for a particular partition, a range, this is the way to make sure that all of the data is consistent. Why would data not be consistent? Well, stuff happens. A node is seen as down for whatever reason, network issue, or data centers will lose connectivity. Right? In order to be a fault-tolerant system, we have to have these types of systems in place. Now, seemingly, even in a non-volatile scenario, there will be a need for repair. What happens is that, that's the definition of entropy. Shit happens, right? Something happens, and one data update is not sent to one of the nodes. That's why we have to go through and comprehensively make sure that everything is clean. This is one of the major gripes of people that operate on Cassandra when they don't use Reaper and when they don't use Op Center is, oh yeah, we have to do repairs. Or some people don't even do repairs. I'm like, when's the last time you ran a repair? Like, oh, I ran it 6 months ago. And I'm like, oh my God, I can't believe that. You should be doing it pretty much every week. So that's kind of the topic for today, which was, repair, anti-entropy. Any questions about repair or what it is and why we need it? Okay. If not, we can go ahead and wrap up for today. I can give you guys back 20 minutes of your day. Join us back here, same time, same place next week. Next week, I'm going to be covering probably tombstones. Let me see what's in the queue here. Oops. Tombstones, yeah. We'll cover tombstones, and what tombstones are and why we need to avoid them, and we'll keep going. Thanks, guys. Have a wonderful rest of the day. Talk to you soon.